Hi, I'm Tim Eastridge, and I'm author of Graph Data Science with Python and Neo4j. I'm founder of Eastridge Analytics LLC based in Charlotte, North Carolina, where we specialize in graph data science for use cases like entity resolution, fraud detection, and supply chain management. Today, I'm excited to showcase a new app in Snowflake to gather graph data science algorithms and run them directly in Snowflake with no ETL required. The company Neo4j just launched this app last week, and I'm excited. As many of you already know, graph algorithms open a whole new world of analytics, including graph-based machine learning, centrality to identify the most important nodes in a network, community detection to identify points which are grouped together in a cluster, and pathfinding to identify the most optimal path between data points. Up until now, the best and really only available method at scale to run graph analytics was to import the data within a native graph database such as Neo4j. However, thanks to the partnership between Snowflake and Neo4j, we're now able to run algorithms directly in Snowflake. So you now get access to the algorithms without all the complex ETL and without duplicating data storage requirements. Let's take a look. All right, so first, let's take a look at this article written by people over at Snowflake to showcase this new app. So we pull up this article in medium.com, and we can see we need to download Neo4j from the marketplace, import the data, run the app, run the algorithms. So I'll go ahead and run through all of these. These grant permissions, and they tell it which database to use and which schema to use. So I'll go ahead and run that. You need to import your data into a database over here on the left. So I set up a temp database, public, tables, and you can see these P2P users, P2P transactions, and so that's what we're going to use today for the demo. So now after this completes, we'll come down and look at the two primary tables for today's demo, where we're going to group together P2P, which stands for peer-to-peer. You can think Venmo, Zelle, Cash App, some of these that allow us to transfer money peer-to-peer. So P2P users will show some data that Neo4j provided for this demo, and then P2P with shared cards is a table that shows which users are also have the same credit card on file. And so there'll be a link between different users. And so we can do community detection on shared users because there's connections between users, and so it creates this community cluster, right? And with that community, we could resolve to say, wait a second, this is the same entity. So maybe someone has multiple accounts. You want to roll that into the same family group and say this is an entity. That reduces the number of fraud alerts that you might have. It improves your analytics and marketing capabilities. So we can do entity resolution. And then the other thing we're going to do is node centrality. So node centrality says within this community of nodes, which ones are most central or most important within the community. So let's go ahead and take a look at this first table, P2P users. And we can see here there is a node ID, which represents the customer ID, a fraud transfer flag, so a flag of 1 or 0 if this customer is associated with fraud, the number of IP addresses linked to that customer, the number of cards, and the number of devices. And then next we have the shared card information. So this links together different customers based off of starting with this node, we're going to link to this node. So it's a little bit more difficult to conceptualize this, especially with all the numbers. So let me show a visual representation. So in this visual representation, this is using the Neo4j browser tool. We can see that here's a customer ID. So here's a customer that has one card. We have a centrality score, which we'll show that in a moment, how we generate that. We have a device count, a fraud flag, IP count, and then this is the community ID, and we'll come back to this in a moment as well. So this node is showing up as green because it does not have fraud. Fraud is 0. This one's showing up as red because it does have a fraud flag here. And so going back to this table we looked at before, these are the linkages between the different nodes. So you can think of these as these what we call relationships or edges between nodes. So before, we would have to import all of this data into Neo4j in order to run things like community detection, where we can say all of these customers are part of the same community, and we want to find communities that have high risk of fraud or have high profit values, right? So there's different metrics that we can run within the communities, but it required ETL, extract, transform, and load, where we would have to pull the data from our relational database like Snowflake and push it into a different database like Neo4j to run these algorithms. Now we can just run it directly within Snowflake. So I'm going to say select entity linking graph, that's the variable name. And then we need a node table, which represents all the nodes that we want to push into our graph algorithm. And we need a relationship table, which represents all of the edges or relationships between those nodes. So let's go ahead and run this. This will do. Great. So that wrote 33,000 nodes, 6,000 relationships, and with that graph now in memory, we can run the PageRank algorithm. So the PageRank algorithm is a commonly used node centrality algorithm that links together nodes, and it was developed by Google to identify the most central web pages and assign a value to the relative importance of each web page. So we're going to mutate the graph projection to save the score of the PageRank algorithm. And then we're going to write that mutated result to a Snowflake table. So here we're going to say write properties from this graph projection score to this table name. So go ahead and run that. Great. No errors. Properties exported, 33,000 properties. Now we can view those properties here. So we can see that this node ID is the most central node within the graph. The next thing we're going to do is add PageRank as a column to the table. So I'm going to alter that table, add centrality, and then update it. We're going to round it to 3 decimal points. And we can go back and look at that table here, P2P users. So now we can see the centrality score here. So this is a node ID with the centrality. And as you scroll down, you can see some of the nodes have higher centrality points if they're linked to multiple other nodes. All right, and the next thing we're going to do is run the WCC algorithm for community detection. So WCC stands for Weakly Connected Components. And basically that just means if there's any link between any two nodes, let's group them together and assign a community ID to all linked nodes. So if I have a family of 100 people, they're all going to be linked together through different relationships, and they're all going to be assigned the same family ID. So I'm going to go ahead and run this here to mutate the graph projection and assign a WCC ID. You can see it runs very quickly. It created 29,000 communities with the max size being 36 nodes within the community. I'll go ahead and run this to write that to a new table called P2P components. And then we can run this to view the P2P components table. And now we can see that this node is in community 8. And then both of these customers are in community 9. Both of these customers are in community 11. Okay, now we're going to update the P2P users table with that component ID. So then we'll go back here and show that community table again. Okay, so now we have the different customer IDs here, and then you can see the centrality and then also the community ID here. All right, create a resolved entity view based off of WCC. So now let's create a table that illustrates the number of fraud flags within each community, and take a look at that. And then I'm also just going to add a row ID to the edge table, relationship table, just for visualization purposes. And then let's take a look at this resolved P2P user step. So again, this is up here, we say create resolve P2P users. We're going to group by the WCC ID and say how many users are there within the community. And then if there's a fraud transfer flag, let's sum up the number of fraud transfer flags and write that to the table. And then we're going to create an array of all the user IDs within the community. So this community, 433, has 23 users, has 3 fraud flags, and then here are all the user IDs within that community. So I'm going to come over here, and this is a Cypher query that was originally developed by Neo4j. They have an open Cypher option as well. And Cypher allows us to write these graph patterns similar to SQL, but in a different way that interacts directly with graph. And so this image is rendered directly off of querying the Snowflake data. So there's no ETL required, but we're able to visualize this community number 433. So I'm going to come back over here, and you can see there's 23 users and 3 fraud flags. We can see that here. There's 3 fraud flags. Fraud has a flag of 1. And then we can also see the centrality score. So here there's a centrality of 0.37 linked to 0.54 and 0.55. And then right here in the middle is 1.17 as the most central node. And then again out here you can see 0.43 linked to 0.67 to 1.07. So it gives us a feel for how central within this community, and again, all of these are in the same community number 433. Each of these that I click is part of community 433, but some of them are more central based off of their relationships to other nodes. Then just do some cleanup steps, and then we need to make sure that we drop the graph projection, and then we stop the session. So that wraps up our demo for today. I hope that you all found this to be helpful, informative, to illustrate how we can now run graph data science algorithms directly within Snowflake. If you have any questions, please don't hesitate to reach out, info@eastridge-analytics.com, or our website is www.eastridge-analytics.com. Thank you. Have a great day.